Greetings, everybody. Learning is a hobby here. I wanted to get around finally to section 3.6, my summary for section 3.6 in Tao's Analysis 1 book. So let's jump into that. And then we'll only have one more video left for chapter 3, which would be the exercise set for 3.6. So, like I said, let's jump into it here. Okay, so section 6 in chapter 3 is about cardinality of finite sets. Oops, why did I get smaller? Right, there we go. So he says in the beginning of the section that the piano axioms, which we looked at in chapter 2, if you remember, the piano axiom approach treats natural numbers more like ordinals rather than cardinals. Cardinals are used to count how many things are in a set. So, for example, 1, 2, 3 things or whatever, right, in a set, or objects or elements in the set. The ordinals are used to order a sequence of objects. So, first, second, third, etc., etc. There's a subtle difference between these notions, especially when comparing infinite ordinals and infinite cardinals, which will not be treated in this text. So then we jump into definition 3.6.1 about equal cardinality, what it means for two sets to have equal cardinality. We say that two sets, X and Y, have equal cardinality if and only if there exists a bijection, F from X to Y. Now, this definition actually we'll use for not only finite sets of finite cardinality, which we'll define in a little bit, and sets of infinite cardinality, which is actually something that we'll look at in chapter 8, so way down the line. But that's the definition for what we mean when we say two sets have equal cardinality. All right, he gives an example here, example 3.6.2. The sets 0, 1, 2, the set containing 0, 1, 2, and the set containing 3, 4, 5 have equal cardinality because we can set up a one-to-one correspondence between them, or in other words, a bijection. He says, note, we do not yet know whether the set containing 0, 1, and 2 and the set containing 3 and 4 have equal cardinality. There may still be some bijection between them, even though, the obvious one, an obvious function between them, would not be bijection, but there may be one that works. It turns out that cardinality is not equal, but this will be proven later on once we have some more definitions and theorems. Okay, another note here. This definition makes sense regardless of whether X, Y are infinite or finite. I just mentioned this actually up above. We haven't even defined what finite means yet, but we will. Right, in Mark 3.6.3, the fact that X and Y have equal cardinality does not preclude one being a subset of the other. For example, if X is the natural numbers and Y is the set of even natural numbers, then X and Y have equal cardinality since f of n equals 2n is a bijection. And then, he asks, why is that a bijection? So I just proved that it is down here. So in other words, if f of n equals f of m, that means that 2n equals 2m, which means that which means that n equals m, and it's surjective because if you take any even natural number, then m equals 2n for some n in the natural numbers. However, notice that the even natural numbers is a subset of the natural numbers. In fact, a proper subset of the natural numbers. Right, another note, equivalence of cardinality is an equivalence relation, which is what proposition 3.6.4 says. So here he says that sets having equal cardinality is symmetric, reflexive, and transitive. So, it's an equivalence relation, in other words, and he leaves the proof for the exercise set. So we'll take a look at that one in the video when we do the exercises for this section. All right, definition 3.6.5, let n be a natural number. A set X is said to have cardinality n if and only if it has equal cardinality with the set of all natural numbers I, where I is between 1 and n. We also say that X has n elements if and only if it has cardinality n. All right, remark 366. One can use the set of all natural numbers I, where I is strictly less than n, instead of the set of all natural numbers I, where I is greater than or equal to 1, less than or equal to n, since these two sets have equal cardinality. Now, in the book, he asks why, so I proved that statement down here. So this is not in the book. It's one of those things where he asks the reader, to supply the reason why. So here's my proof. Let F be the set I in n, where I is less than n. Let F be the function from the set I in n, where I is less than n, to the set I in n, where I is greater than or equal to 1, less than or equal to n. And let it be the function that takes n to its successor. Then F is injective by axiom 2.4. Also, F of the set just containing 0. So the image of the set containing the number 0 under F is equal to the set containing just the successor of 0, which is the set containing 1, the singleton set containing 1. And if the image of the set I in n, I less than n, under F is equal to the set of all I in n, where I is greater than or equal to 1, less than or equal to n, for some n in n, then F, the image of I in n, I less than the successor of n, is equal to F of the union of the set of all I in n, I less than n, union with the singleton set containing n, which is equal to the union of the images there. That follows from an exercise that we did a little while ago. That's equal to the union of the set I in n, where I is greater than or equal to 1, less than or equal to n, union with the singleton set containing the successor of n, which is the union of those two sets is equal to the set of all I in n, such that I is greater than or equal to 1, less than or equal to the successor of n. Since F is injective, and the exercise I'm referring to is exercise 343, which we did a while ago. So if you don't remember that one, excuse me, should have gotten some water. If you don't remember that one, you can look back at the video. That's we did that exercise a few videos back. Okay, example 367. Let A, B, C, D be distinct objects. Then the set containing A, B, C, D has the same cardinality as the set of all I in n, where I is less than 4, which is the set containing the natural numbers 0, 1, 2, 3, or I is an element of n, where I is greater than or equal to 1, less than or equal to 4, which is a set containing the natural numbers 1, 2, 3, 4, and thus has cardinality 4. Similarly, the singleton set A has cardinality 1. Okay, here's a lemma that we'll use to prove the next proposition. So the ordering, the numbering here, you'll notice is backwards because he states the proposition first, and then he says the lemma, and then proves it, and then uses that to prove the proposition. But I did it in reverse. I just think it makes more sense, to do the lemma first and then do the proposition. So I just reversed the order. So this is lemma 3.6.9 from the book. Suppose that n is greater than or equal to 1 and x has cardinality n, then x is non-empty, and if x is any element of x, then the set x minus the singleton set containing x, that's set difference there, by the way, has cardinality n minus 1. And then just a note here, treat n minus 1 as the unique natural number m, such that n is the successor of m, since we haven't formally defined expressions like n minus 1 yet. We haven't talked about subtraction, in other words. So all it means is n minus 1 just means it's the predecessor of n, if you want to think about it like that. Okay, so here's the proof. Assume x is empty. Oh, I should say also the proofs of the propositions in this section. A lot of them he leaves sort of the exercise set, but also even the ones that he supplies in the book are only partial proofs. There's a bunch of statements in the proofs that he asks you to supply the reasoning for. So rather than sort of stick to my own proofs, I used his proofs and filled in the details just to be consistent with whenever in the book he says why, I like to do that, explaining why. So there are parts of this proof where he doesn't actually do it in the book, but he asks why. So I'll point them out when I talk about it, but just be aware of that. So assume X is empty. Then there's a bijection F from X to the set of all I in N, such that I is greater than or equal to 1, which is less than or equal to N. However, this means that 1 is equal to f of x for some x and x, contradicting that x is empty. Therefore, x is not the empty set. So it's not, in other words, it's not empty. That's one of the things that he doesn't really show. He just kind of just says, if x is empty, it has the same cardinality. If x has cardinality 0, it has the same cardinality as the empty set. And there's clearly, he just says there's no bijection between that set and a set containing some, having positive cardinality. So here I actually supplied, I guess the details. Next, since X has cardinality N, there's a bijection F from X to the set of all I in N, such that I is greater than or equal to 1, less than or equal to N. Define the function G such that G is equal to X, where G takes the set X minus the singleton set X to the set of all I in N, such that I is greater than or equal to 1, less than or equal to N minus 1, or if you like, the predecessor of N. Here's the way you define it. So let G of Y be f of Y if f of Y is less than f of X, and f of Y minus 1 if f of Y is greater than f of X, right? Then he says G is a bijection, but he doesn't prove it. He says you should prove it. He said, this is one of the places where he says why. So this is my proof that G is a bijection. So first I showed that G is injective, which just follows directly from the fact that F is already injective. And then from part B, G is surjective for any M in the set I in N, where I is greater than or equal to 1, less than or equal to N. M equals f of Y for some Y in X. If f of X equals N, then G of Y equals f of Y for all Y in the set X minus the singleton set containing X, which implies that G is surjective. So that's sort of like the first case. Then the second case would be if f of X is less than N. Then if M is an element of the set of all I in N, such that 1 is less than, 1 is less than or equal to I is less than f of X, that implies G of Y equals f of Y equals M for some Y in the set X minus singleton set X, and M prime, an element of the set I in N, for which f of X is less than or equal to I less than N minus 1. Actually, this should be less than or equal. Sorry, let me fix this. Whoops. Why is this not writing? All right, I don't know why it's not writing. That should be a less than or equal to N minus 1. Right, that implies that f of X is less than the successor of M prime, less than or equal to N. Which implies that the successor of M prime equals f of Y for some Y in the set X minus the singleton set X, which implies the successor of G of Y equals the successor of M prime, which implies that G of Y is M prime by axiom 2.4. Therefore, that means G is surjective. And those two cases cover everything. So that shows that G is a bijection. And okay, and that's the proof of the lemma. All right, let's look at proposition 368 then, which will rely on the lemma that we just proved. Let's look at the statement first. So proposition 368 states that the uniqueness of cardinality, or in other words, let X be a set with some cardinality N, then X cannot have any other cardinality. So cardinalities are unique. All right, so we do this with induction. So induct on N. Here's the base step. Let the cardinality of the set X be 0. Then X has equal cardinality to the empty set. Assume X also has cardinality N greater than or equal to 1. Then there's a bijection F from the empty set to X and a bijection G from X to the set I and N, such that I is greater than or equal to 1, less than or equal to N. Then the composition G with F of the empty set, that takes the empty set to the set of all I and N, such that I is greater than or equal to 1, less than or equal to N is a bijection by exercise 332. This is something that I filled the details in. Also, he doesn't state all the details here. He just says that it can't happen. So, but that's, I filled in the details here. Then that would imply that one is G composed of f of x or some x in the empty set, which contradicts that the empty set is empty. So that's the base step. The base step is satisfied. Then we go on to the inductive step, and here's where we're going to need the lemma that we just proved a few minutes ago. Assume any set with cardinality n has unique cardinality, then the set, let x be a set with cardinality the successor of n, then x is non-empty by lemma 369. If x also has cardinality m, and x is an element of x, then the set x minus the singleton set containing x has cardinality m minus 1 and cardinality n, and cardinality n. That follows from the lemma 3.6.9 again. So, however, the inductive hypothesis then implies that n is equal to m minus 1. Therefore, the successor of n equals m by axiom 2.4. And the proposition follows then by principle of mathematical induction. Okay, definition 3610. Now we can define finally what we mean by finite sets. So a set is finite if and only if it has cardinality n for some natural number n. Otherwise, the set is called infinite. If x is a finite set, we use this symbol here, so number of x, I guess you could read it, to denote the cardinality of x, or you could just read it as cardinality of x, I guess. Right, example 3611. Is that 3611? Example 361? No, it should be 11, I think. Kind of looks like a parentheses there, but okay. Anyway, the sets 0, 1, 2, and 3, 4 are finite, as is the empty set 0, because 0 is an unnatural number, and the cardinality of the set containing 0, 1, 2 is equal to 3. The cardinality of the set containing 3 and 4 is 2, and the cardinality of the empty set is 0. Right, then we have a theorem. The set of natural numbers n is infinite. So here's the proof. Assume n is finite, then the cardinality of n is n for some natural number n. So we can do this by contradiction. Or actually, did I do it by contradiction or? Yeah, I did. Okay. Assume n is a natural number, then the natural number. Sorry, let's start this over. Assume n is finite, then the cardinality of n equals n for some natural number n. Then the cardinality of n minus the singleton set containing 0 is n minus 1. However, if you look at the function f that goes from n to the set n minus the singleton set containing 0, where f of n is the successor function, that's a bijection. Since here I'm proving that it's a bijection, f of n equals f of m implies successor n equals successor m, which is n by n, which implies n equals m by axiom 2.4. And if the successor of n is an element of n minus the singleton set containing 0, then f of n equals the successor of n, since 0 is not an element of n minus the singleton set containing 0, right? 0 is the only natural number that doesn't have a successor. Therefore, n minus 1 is equal to the cardinality of the natural numbers minus the singleton set containing 0, which is equal to the cardinality of the natural numbers, which is equal to n, or in other words, that implies that n minus 1 equals n, but that contradicts proposition 3.6.8. Therefore, our assumption was false, that, our assumption that n was finite was false, therefore it's infinite. Right? Remark 3.6.13. One can also use similar arguments to show that any unbounded set, he defines unbounded sets in definition 9.1.22, which that's all the way in chapter 9. So that's something we'll get to, way in the future. Sorry, you can use similar arguments to show that any unbounded set is infinite. For instance, the real numbers and the rational numbers, which we'll define in the next two sections, are infinite examples of infinite sets as well. So are the integers. However, it is possible for some sets to be, he says, quote unquote, more infinite than others. See section 8.3, because that's when we'll talk about cardinalities of infinite sets. All right, so there's, you may or may not know this fact already, but there are infinities of different sizes. So we'll talk about that in chapter 8. Right, here's proposition 3.6.14, which is on cardinal arithmetic. So let's go through each of the different cases here. Let X be a finite set and let X be an object which is not an element of X. Then X union the singleton set X is finite, and the cardinality of X union the singleton set containing X is equal to the cardinality of X plus 1. Right? Part B says let X, Y be finite sets. Then X union Y is finite, and the cardinality of X union Y is less than or equal to the cardinality of X plus the cardinality of Y. If in addition X and Y are disjoint, which means X intersect Y is empty, then the the cardinality of X union Y is equal to the cardinality of X plus the cardinality of Y. Okay, property C. Let X be a finite set and let Y be a subset of X, then Y is finite and the cardinality of Y is less than or equal to the cardinality of X. If in addition Y is not equal to X, then the cardinality of Y is strictly less than the cardinality of X. Right, part D. If X is a finite set and F is a function from X to Y, then f of X, the image of X under F, is a finite set with cardinality of the image of X under F less than or equal to the cardinality of X. One has equality if, one has equality, the cardinality of the image of X under F equals the cardinality of X if and only if F is 1 to 1. So if it's injective, then it's equal. Property E. Let X and Y be finite sets, then the Cartesian product, X times Y, is finite, and the cardinality of X times Y is equal to the cardinality of X times the cardinality of Y. And finally, part F, let X and Y be finite sets, then the power set Y to the X is finite, and the cardinality of Y to the X equals the cardinality of Y raised to the cardinality of X. Right, and the proof for this he leaves for the exercise set, so that's something we'll take a look at when we get to the video on the exercises. Okay, we're almost done. There's just a couple more things to say. Remark 3.6.15. Proposition 3.6.14 suggests there's another way to define the arithmetical operations of natural numbers, not defined recursively as we did in chapter 2, so definition 2.2.1, 2.3.1, and 2.3.11, but instead using the notions of union, Cartesian products, and power sets. This is the basis of cardinal arithmetic, which is an alternative foundation to arithmetic than the piano arithmetic we've developed here. However, he says in the book, we will not develop this arithmetic in this text, but we'll give some examples of how one would work with this arithmetic in exercises 3.6.5 and 3.6.6. So again, when we get to the exercise set, that's something we have to look forward to. Okay, and then finally, this concludes our discussion of finite sets. However, Tao does discuss infinite sets in chapter 8. So once we have some more examples of infinite sets under our belt, like, for example, we're going to construct the set of integers and the set of rationals in chapter 4, and we're going to construct the real numbers in chapter 5. So once we have more examples of infinite sets, then in chapter 8, we'll talk more about infinite sets there. So later on down the line. Okay, and that's the end of my summary for for section 3.6. So let me just stop sharing my notes for a second. Okay, so that's the summary for 3.6. 3.6 is the last section in chapter 3 here. So all we have left to do in chapter 3 is the exercise set for 3.6, and then we're on to chapter 4. The only thing is the exercise set for section 3.6 is a little bit long, so it'll take me probably going to take me a little bit of time to get through the exercise set there. But then once we're done with that, we can finally get onto the construction of Z, Q, and R in chapter 4 and chapter 5, and then once we finish that, we can come back around to Spivak and look at the Dedekind cut construction, and then continue with what we were doing with we haven't even started on derivatives in Spivak yet, but we will after we do the construction of the real numbers, both with Cauchy sequences and with Dedekind cuts. Okay, so thanks for watching, guys. If you made it this far, I'll try to have the video for the exercise set for section 3.6 out sometime this week. I don't know how long it's going to take me to get through I haven't even looked at the exercises yet, but I don't know how long it's going to take for me to get through them, but hopefully by next weekend, the video for that will be out. And then I'm looking forward to chapter 4 to get a little bit of a change of material here. So I'll see you guys in the next one. Keep learning, everybody. Let me know what you think down below in the comments section, and I'll see you in the next video. Keep learning, guys.